Hello, in this video we're going to be taking a look at solving trig equations of the form sine of ax equals, cos of ax equals, and tan of ax equals, where a is just going to be a number. Now this a in front of our x is actually going to transform the graph, and it's going to be a stretch parallel to the x-axis, and I've got a really nice visual that I'm going to show you in a second that's going to show you what's happening when this transformation takes place, and hopefully help you make a bit more sense of what we're doing when we're solving these equations. Now in this video I'm going to work through 3 different examples and I'll timestamp each one of them below, and if it's useful please do go over to my YouTube channel where I've got loads of other maths tutorials, as well as my website which I'll link in the video description, where you can see all of my videos in one place. So in the start I said that the a in front of the x is a transformation that's happening to the trig function, and I just want to do a couple of examples to demonstrate what that transformation is in case you're not too clued up on graph transformations. So say we start off with a standard trig function, let's say f of x equals sine of x. Now we know the period of sine of x is 360 degrees, don't we? It's just what we've looked at earlier. It's how often it repeats or cycles. Now let me apply a transformation to this graph. Let's look at, say, f of 2x. Okay, so now I'm looking at the function sine of 2x. Well, what is this 2 in front of the x doing? What this is doing is stretching the graph, scale factor 1 over 2, parallel to the x-axis, and I'll put a visual on screen now as the coefficient of x changes from 1 to 2 so you can see this stretch taking place. Now what this means is that the period of the graph is going to halve. It's going to become half as much. It's going to kind of get squished twice as much. And so the period of the graph is also going to halve, and you can see that from that visual. So the period is halved, so now if we're looking at sine of 2x, the period has changed from 360 degrees to 180 degrees. Now understanding this is going to help with the method I use to solve the trig equations we're going to look at today. And so to make sure you've really got this, I'm going to do 2 more very small examples. Say we had cos of 3x, what would be the period of this function? Well, there's a 3 in front of the x, which means it's being stretched, scale factor 1 over 3, parallel to the x-axis, and so the period is going to be 3 times smaller. And so the period of cosine of 3x is no longer 360 degrees, we divide it by 3, so it's going to be 120 degrees. And one final example, say we had, for example, tan of 1/2 x. Well, the original period of tan is 180, but what we're doing is we're stretching it scale factor, well, 1 over 1/2, which is 2, so it's going to become twice as much. So the period is now no longer going to be a half, it's going to double, and the period is going to become 360 degrees. So if you can understand this, the rest of the video should be pretty straightforward to do. So let's look at our first question, where we have to solve sine of 2x equals 1/2. And we're solving it on the interval between 0 and 180 degrees. So the first thing we're going to do is kind of ignore the 2x and the interval, and we're just going to sketch sine of x. And in fact, for every trig equation we solve, we're always just going to sketch the original function that we looked at the start. So sine of x in this case. And so I'm going to sketch out my graph. So there's 90, there's 180, there's 270, and there's 360. I'm now going to do inverse sine of 1/2, and that's going to tell me what 2x is equal to. So let's do that. That's going to be 2x equals inverse sine of 1/2. And if you type that in your calculator, or maybe you know it, 2x is going to equal 30 degrees. And so we can sketch that or put that onto our graph. So I know that, well, it equals 1/2 here at 30 degrees. Now because of the symmetry, I know, well, if I've gone 30 degrees to the right of the origin, well, if I go to 180 and I go back 30 degrees, there's going to be another solution there, and that's going to be at 180 minus 30, well, that's 150 degrees. So let me write that down as another solution. 2x could also equal 150 degrees. Now we've got these 2 solutions, remember we're solving sine of 2x. And so actually if I was to try and sketch out sine of 2x on the graph I've got now, it's going to be twice as compressed, isn't it? It's going to be half as long as it was before. It's going to look something like this. So I need to halve both of these solutions, and when I do, they're going to move onto the curve that's been translated by a scale factor of 1/2. And I've got a really nice visual that I'll put on screen now to kind of demonstrate this happening. So when I halve both of these, I'll just get rid of all this extra annotation. When I halve both of these, I'm going to get x equals 15 degrees and also x equals 75 degrees. Now, a common misconception is people just find this solution, they divide it by 2 and get x equals 15, and then they do 180 minus 15 and use that as their second solution. But I'll put a visual on screen now that will hopefully kind of show you graphically why this doesn't work. Because I can see why people do it, but unfortunately that's not going to give you the right answer. So with all of these, and in fact all trig equations we're going to solve, do the inverse sine or cos or tan, whatever it is, find the other solution in that initial period, and then solve both of the equations to make x the subject. So we've now got the two solutions in the initial period of the function that we were interested in. Let's now think, what is the period of sine of 2x? Well, hopefully you can remember from the start, the period of this graph is going to be 180 degrees. It's halved, hasn't it? It was 360, the 2x has stretched it scale factor a half, and so now the period is 180 degrees. So to search for any other solutions, all we're going to do is take the solutions that we've just found and add or subtract 180 degrees from them and see if there's any others in this interval. And actually you can already tell that if I add 180 to 15, I'm outside the interval, I'm at 195. The same for x equals 75. If I add 180 to it, I'm beyond 180 degrees. And it's also the same scenario if I subtract them. So that's it, there are only two solutions for this equation. Let's now look at the second example, where here we're asked to solve cosine of 1/2 x equals root 3 over 2. And we're solving it on the interval between 0 and 540 degrees. So let's think, what is this half doing? Well, that's stretching the graph of cos x, scale factor 1/1/2, so scale factor 2, parallel to the x-axis. And again, I'll put a visual on screen to show you the graph stretching so it's twice as long. But remember, for now, we're not actually going to worry about any of this. All we're going to do is sketch the graph of cosine of x. So let me draw out the graph. Here it is. And so cos starts at 1, it goes down to -1, comes back up to 1. So we've got 90, 180, 270, and 360. From here, I'm going to do inverse cos of root 3 over 2, and that's going to tell me that 1/2 x is going to equal inverse cosine of root 3 over 2. And so if you solve that, either you know that value or you do it on your calculator, you get 1/2 x equals 30 degrees. Now, before you try and solve this for x, like a lot of people do, remember there's going to be another solution within this initial period. So we found one of them at x is 30 degrees, so here. Now there's going to be another one over here at 360 minus 30 degrees, so at 330 degrees. So it's also possible that 1/2 x equals 330 degrees. Now we found the two solutions in that initial period, we can solve to make x the subject. So times both sides by 2 and we get x equals 60 degrees. Or on this side, if I times both sides by 2, I get x equals 660 degrees. Now let's think, what is the period of cos of 1/2 x? Well, this is a stretch scale factor 2, and so the period's going to double. So it was 360, the new period of this graph is now going to be 720 degrees. That's quite a large period. Now hopefully you can see I don't need to add or subtract the period from either of these solutions because it's going to be well outside of the range once I do that. And so what we can do is just look at these two solutions and see if they lie in our interval. Well, we can clearly see that x equals 60 does, but actually x equals 660 does not. And so what we'd do is put a cross through it and reject that solution. And that's this question done. Let's now look at the final example we're going to look at, which is to solve tan of 3x equals 2 between 180 degrees and 250 degrees. So the first thing I'm going to do is sketch out the graph, and I'm going to do that just for its initial period from 0 up to 180. You don't really need to worry about too much more for tan, just that first initial period will pretty much always do most of the time. Next, we're going to do inverse tan of 2, and that's going to tell us what 3x is equal to, so inverse tan of 2. And to three significant figures, that tells me that 3x is equal to 63.4 degrees. Now tan is quite a nice one because remember, and I said this in the previous video too, with sine and cosine there are two solutions in that initial first period. But with tan there's only one solution per period, so actually from here you can divide by 3 straight away. You could, if you wanted to, add on 180 degrees to this solution, then divide them both by 3. But remember, like we've said, because there's only one solution in each period of the graph of tan of x, you don't need to worry about it. So we can go ahead now and divide both sides by 3. And if I divide 63.4 by 3, it's going to give me 21, let's say 0.1 degrees, to 3 decimal places. Now, the original period of the graph of tan of x was 180, but what we've done, remember, is we've stretched its scale factor a third, so it's 3 times as compressed, and so the new period is 60 degrees. So now I'm going to take this solution that I've got here, this initial solution, and I'm going to keep adding on 60 to it until I find my solutions that lie within this interval. So if I add on 60, it gives me a solution of x equals 81.1, which is obviously not in the interval. I'm going to add on 60 again, which gives me a solution of x equals 141.1, which is not in the interval, so I'll add on 60 again. This gives me another solution of 201.1 degrees, which is within my interval, so I will accept that solution. And if I add on 60 again, well, I get x equals 261.1, which is now again outside of my interval. So I'll reject all of these other solutions because they're not relevant to me anymore, and I'll just highlight the one that I want. So hopefully this video was useful. If it was, please do go over to my channel where I have loads of other maths tutorials, and you can also go over to my website, which I'll link in the video description, where you can see all of my videos in one place, and it's a bit easier to navigate them than it is on YouTube. Thanks for watching.